All right. Hello, everyone. Welcome to this week's Corundum developer meeting. So today I got a bunch of updates for you guys. I've had a rather productive couple of weeks over here. So lots of little things got done. So let's get into the status updates. All right. So over the past couple of weeks, well, I guess more than a couple of weeks, I've added support for a couple of new devices, which I'll mention on the next slide. And then I've done a whole bunch of work on kind of application support. So a bunch of stuff related to that on the software side and a little bit of supporting hardware for that. And then I guess the other thing that I worked on is the RxQ selection components. And I think that is, well, I'm not going to say the RxQ selection is completely done at this point, but we now have the ability to factor in the TDES signal from the application in terms of selecting which receive queue to use. Everything else there hasn't really been too much progress on. All right, so new device support. I added support for two more boards, the Bitware XUP P3R and this Dini Group board. So the Bitware board, this one is somewhat similar to like the VCU 1525, similar form factor, same FPGA, four independent memory channels. But the interesting thing is it has four QSFP28s instead of two. So this is the first board in the repository effectively that is configured with four interfaces by default instead of two. And seems to work just fine, 10G, 25G, and 100G. So that's useful. To do on that is all the BMC integration stuff. There's a couple of annoying things about the way the BMC on that card is set up. It seems like they're doing something funky in terms of how the FPGA boots from flash. They're not using the standard technique that Xilinx details in the configuration user guides and whatnot. And it seems like once it gets into a situation where it's booting from the fallback flash, you have to poke at it over the serial port to get it back to booting, you know, um, normally. And ostensibly that requires tools from Bitware to do that. I've managed to figure out how to do it using libusb from Python. So I need to get my little utility for that cleaned up so you can poke at it from user space, and then also potentially link it up through the hardware on the FPGA as well, because there's also a serial port from the FPGA side. So then you can poke at the BMC over PCI Express. So that's still a to-do on that. And then the other board that I added support for is this Dini Group board. It's got a small Kintex ultra-scale FPGA on it, two QSFP pluses. The idea with this particular board, I acquired several of them a while ago for a pretty reasonable price, and my hope is to be able to provide them to folks that would like to work on Corundum but don't otherwise have access to hardware. Details on that are TBD at this point, but that's kind of the idea. If that's something you're interested in, contact me. Maybe we can work something out. Although licensing from Vivado is still potentially a problem with these because it's the KU40 requires the full software suite. So yeah, we'll see. They're not the ideal board, but they are at least something. So all right, but it does work. Tested it out at 10 gig, and both the interfaces operational. So we're all good with respect to that. Okay, so moving on to application support. I've done a bunch of work on the software components for interfacing with the FPGA design. So the first thing I did is I pulled out a lot of the shared code into a little static library that all of the user space tools can use, and this makes things a little bit easier when you have multiple application directories containing user space tools instead of throwing it all in the same directory. So the way I have the repository set up, I have kind of one main utilities directory for the user space tools just for the general design. And then in the applications folder, what I want to be able to do is create subfolders for user space utilities and kernel modules for specific applications, but still have them take advantage of the shared code at the top level. So by peeling things off into a static library, it makes it a little bit easier to set that up with makefiles and whatnot. So I got that peeled off. I got the makefile support all fleshed out, so that works correctly. Potentially, that can be moved to a shared object later on if necessary. I also went ahead and I added an application ID register block. So the idea with this is you set the application ID in config.tcl, and then that ID gets exported by the core registers, and it's also passed through to the application section. More on that in a little bit and why I went for this particular route. I also implemented the auxiliary bus interface in the main device driver. So this allows a sub-device driver basically for the application section to extend the core device driver. And potentially we can, add some additional interfaces on here and make some modifications. Like maybe it makes sense to have an auxiliary bus interface that's kind of unconditional, that's not dependent on the application section and is always exported. Not sure, haven't, that's definitely something that can be discussed. I also went ahead and added, or I made some updates to the template application that has been in the repository for a while. And then I also added a new application, which is the DMA benchmarking application. So more details on that in a couple of slides. All right, so the static library, a couple details on that. I added this libmqnec.a for common interface code, and this handles the connection to the device, opening and closing the object. And the idea is this will also handle all of the IOCTLs. So you'll never poke at those from the user space application directly. You'll handle the IOCTLs by, calling functions in libmqnec.a, and at which point it will perform the IOCTL, on your behalf. So that way, you don't need to worry too much about the details of what's going on between the user space code and the driver. Eventually, we'll flesh this out with high-level functionality. I've added a couple of things, but still a lot to be done. And potentially, we can switch to a shared object in the future. Not sure if it makes sense. That's something I've done a lot of. The software side, to be honest, is something that I don't have quite as much experience with. So, definitely open to input on the best way of doing things. All right. So moving on, I added the application ID as well. The point of this is to be able to identify what application is running in the application section, and then this will mediate, attaching the user space tools and the and extension kernel modules. So the application ID is simply a 32-bit number that can be used to identify the application section. And what I did is I added an application ID or an application ID register block to kind of the main set of registers that's exported by the core logic. And I also added parameters to the various modules to pass this application ID all the way down to the application block and to this register block. And I've been kind of bouncing back and forth between a couple of different ways of implementing this. My original thought was, okay, let's just have the application module, have like a port or something where it can expose the ID that it wants, and then that gets passed through to the register block, and then you can read it from software. But I ended up kind of changing course on this a little bit because having the application ID in config.tcl has some advantages. And the main one is that if it's in config.tcl, then you can have config.tcl, write it out as metadata that can be included in like a firmware update file or something. So, that this is something on my long-term to-do list is, improving the firmware update file format. If we can include information about like the application block and whatnot in there, then you won't just have some monolithic like what's in this bit file. I don't know, got to load it to find out. You can actually have some metadata that says, okay, here's the application that's installed in there, was built on this date, and yada yada yada. Make things a little bit more user friendly. Additionally, by passing the application ID through into the application section, and this way you can potentially support multiple kind of configurations of an application. So it could look at a few bits in the application ID to determine, how to configure a few things internally, for instance. So there's a couple, I think, advantages of doing it this way. And then obviously the application block can check the value and make sure that it's the one that it expects. And if it isn't, then it will, fail the build. and then you have to fix config.tcl with the correct value. So yeah, that's how that's set up. The application ID is then used by the auxiliary bus to attach the extension kernel module. So the auxiliary bus is a standard method that was introduced pretty recently, actually, into the Linux kernel as a framework for attaching drivers to other drivers, basically. So instead of having, one driver implementing all the functionality for a particular device, you can have auxiliary bus drivers that implement, pieces of it. So what you do is from the main driver, you can register an auxiliary bus device, and then the kernel will manage connecting these extension drivers to the main driver. So when the application section is present, the mqnix driver registers an auxiliary bus device using that application ID. So it just puts it in a hex. Now, originally, I thought you used the .id field for this, but it turns out the ID field is actually just a unique ID thing. So if you're registering, if you have multiple devices, then you can, tell them apart effectively. So we can't use that but it's not used as part of the identification pairing process. That's just for disambiguation. So we have to put the ID inside of the device name, basically. So have an example of what that looks like. The extension modules then register auxiliary bus drivers for their app ID, basically. So you register, a driver for this particular device, and then once both kernel modules are loaded and the device with this app ID is present, then the kernel will automatically, make the connection. Now, the only downside about the auxiliary bus is this was added relatively recently. So if you're running like CentOS or something like that, or Rocky Linux or Red Hat, I don't think this functionality exists in those releases. So I actually honestly have not checked what kernel version is used on the in Peta Linux on the ZC106 design and whatnot. So what we may need to do is figure out, I think we were looking at this before, if it's possible to backport the auxiliary bus support in the kernel, because apparently there's not much to it. And then we can utilize auxiliary bus support as provided by a kernel module instead of as provided by the kernel itself, to handle this, instead of coming up with some other more ad hoc approach. So at least at this point, we now have a couple of applications in the Corundum repository that use the auxiliary bus that we can play with, and try to come up with a solution for some of these older kernels. All right, so that's that. And then we have updates to the example application. So the first one is for the template application. This is just an application block with pass-through logic for all the streaming interfaces, and then it puts an AXI Lite RAM in the application bar. And what I did is I added a very simple user space tool and a very simple auxiliary bus driver that can poke at that RAM. And just as kind of a template, here's what you need to do to, make a user space tool that can connect to a device, and here's what you need to do to make a, auxiliary bus driver that can connect to a device. And then we have the DMA benchmark application that this one has been kind of on the back burner for a while. I wrote it a long time ago, and I've been slowly keeping it. I've been keeping it up to date with changes and whatnot. So all I need to do for this is get basically the driver part working, and then put it in the repo. So what this is a bit of HDL to exercise the DMA engine, including things like strided block transfers and whatnot. And this, so I added this to the repository along with an auxiliary bus driver. And I tried also to write a user space tool, but ran into some issues with the IOMMU. So that is to do on the next slide. But the included driver for the DMA benchmark application, it runs some simple DMA performance benchmarks. So this can be useful just as a sanity check on new hardware. You can, build the DMA benchmark application for that board, run it, and make sure that, you're getting the expected throughput. Just to make sure that the PCI Express interface is working properly on that particular machine. So And the other nice thing about doing this in Corundum is I have another DMA benchmark application or DMA benchmark repository, but this lacks all the firmware update capabilities and whatnot that Corundum has. So by having this inside of Corundum, it makes it a little bit easier to use. It also means that it should work without any additional porting on Intel devices and Zinc devices and whatnot. No, Joachim says Peta Linux uses Linux 5.10. I think that might still be a little too old. I think this was added in like 5.15 or something like that. So yeah, we'll have to take a look at that. Anyway, it should all be set up such that if you try and build the main kernel module with an older version of Linux, it just won't have the application or the auxiliary bus support enabled. It's more like if you need to use that functionality, then we'd have to figure something out. So anyway, at least we have on a working example using the auxiliary bus for now. Then we can circle back and improve that. All right, so the main application related to do at this point is how to support DMA from user space. So I did some experimentation with this using kind of the most direct route. You can determine physical addresses from the ProcFS page map for application virtual addresses, but DMA operations are blocked by the IOMMU. Although I guess it depends a bit on the host system that you're using. Like if you can turn off the IOMMU, then maybe this would work just fine. So I'm assuming that we probably need some help from the device driver, because I know there's like there's some other subsystems that are set up to deal with this, like UIO maybe, VFIO maybe are set up to deal with with handling the IOMMU and whatnot. So we may need to implement something similar to that for Corundum. Not sure. I mean, I guess there's a difference between, running fully user space versus, some Frankenstein combination of user space and kernel space, which, is probably something that people are going to want to do, where you're using the kernel driver to handle the network traffic, and then you have a user space driver to talk to the application. So, this is something that we'll have to figure out. All right, so that's most of the updates in terms of the stuff that I've accomplished over the last couple of weeks here. Let's go over the other couple slides I have here. So PTP clocking updates. I'm going to be taking care of this relatively soon in terms of kind of rebuilding the PTP clock infrastructure to use a separate clock source for the reference clock, probably like a transceiver reference clock, to provide more stable clocks. There was also another question that the I think the MLE guys had about exposing the clock frequency of the core PCI Express clock. And I think what I can do at the same time I do the PTP clocking updates is add some effectively frequency counters and expose that in potentially some sort of a clock information register block that we can use to measure the clock frequency of the core PCIe clock, so you can get a rather accurate measurement for that. Because right now that that clock is not necessarily the most well controlled and predictable. Anyway, so that's on the to-do list. Variable descriptor support. Yeah, this one's been on here for a while. Definitely need to get this squared away. This one's a little bit more complicated to do, so I'm hoping to be able to hammer on this one relatively soon. Oh, I guess I still haven't added a data point to this, or a bullet point to this, but I did get the updated PCI Express subsystem merged in, which supports the immediate write back. And oh, there was also some discussion on the YouTube page for the previous developer meeting, and somebody brought up a couple of good points about the Q pointer write back, and that we might want to be able to pad that out to a full cache line for performance reasons. Not so much because of the transfers over PCI Express, but I guess handling partial Q line writes in the CPU itself can potentially be a bottleneck under certain circumstances. So that's definitely something that might be interesting to take a look at, and that we can take that into consideration when implementing the changes required for variable length descriptor support, and roll in the queue pointer right back and whatnot at the same time. All right, now for the queue selection logic, this one, I think we have this working now. I did a bit of kind of reorganizing to get the queue selection logic to sit inside of the RX engine effectively. And the idea is that when a packet receive operation completes, in terms of the packet is sitting inside of the internal scratchpad RAM, then it will send the receive engine will send a request through the queue mapping module, which will take the TID, TDEST, and RSS hash fields and compute what the destination queue is. So there's 3 parameters that are specified on a per port basis: application mask, RSS mask, and offset. And then they are combined together using the masks to determine which parts of TDEST and RSS hash are used. And then all this added together with the offset to determine the destination queue. And this now works in hardware. I need to test across all of the various boards, all of the various targets, to make sure that everything is working before I push that into the core repository. But at this point, at least I think the folks at MLE can start hammering on this and see if it's going to work for their use case. All right, and then let's see. Next up, management softcore. This one has kind of been backburnered, but yeah, I'm hoping to get this integrated relatively soon so we can use this for file management type stuff. Another thing that we've had a couple of discussions on, I think Emily brought this up last week, and they opened up an issue a couple of days ago, is to implement some PHY status registers. So I've been kind of waffling on the best way to implement the PHY control stuff. So pushing things into the softcore, I think, is going to be the most flexible, right? Because you can have the softcore, act as a man in the middle between, whatever the driver wants to see and whatever the PHY and MAC components are using expect on their register interface or what have you. But I can definitely see the use case for exposing at least a small amount of information in a standardized way. And potentially this just boils down to, like RX and TX status effectively. So one thing that the Xilinx 100 gig Mac has is they have a whole pile of RX status related signals. They have like 20 different lane block lock signals. They have FEC block lock, yada yada yada, but it all boils down to a single RX status pin. So what I don't really want to do in Corundum is like add 500 different PHY related signals passing through the design. But what I could definitely see doing is adding at least a couple of, RX and TX status, something like that. Just from whatever physical layer components you have, just straight into some standard, port related registers internally that are always going to be present that the driver can poke at. So I think I could definitely see doing something like that. Adding a lot of additional stuff, auto negotiation status, current speeds and whatnot. That's a little bit more wishy-washy as to what's going to make the most sense there, and the what that interface might look like. So potentially we can add the RX and TX status signals for now, and then circle back on potentially adding more stuff a little bit down the road. So I guess the other thing too is exactly where these registers are going to sit in terms of the HDL hierarchy, and also the register space. I have some ideas about that, but we might need to revisit that. Topic for discussion. Yeah, and then we have 10G25G switching. Like I said, this is working in hardware using user space software to control it. But we need to move this to the softcore firmware. So this is blocked on getting the softcore operational to get this squared away. Yeah, let's see. And then going back to finally the to-do list for the stable release. Let's see, we haven't made much progress on this yet. We got the application section squared away, register space reorg is done. Application or the shared interface data path, there is still some flow control work that needs to be done, but for the most part, the reorganization is done for that. Self-contained checksum offloading. Need to do some work on on a new parsing module to support that. So that has not been done yet. Variable length descriptor support, that's still to do, and then the FPGA, the management softcore is still to do as well. So still a lot of stuff to do, but got a fair bit of stuff done over the past couple of weeks. So that brings me to the end of the status updates. Now we can open it up for questions and discussion. Does anybody have any questions on anything? Don't everybody speak at once.
So I want to tell you something. I've seen a driver which was all is implemented on user space. It guys from Technical University of München did that. I think it might be similar to DPDK. I don't know DPDK, but they just enable bus mastering and do things like, as you said, they use page map to translate virtual addresses to physical addresses and send to FPGA or their NIC. Using that method, they can do anything. They can implement everything in user space.
Right. So how are they connecting to the hardware? Are they using like UIO or VFIO? I think there's at least a couple of different kernel interfaces that are available for user space to talk to hardware.
They just map some address at a page, huge page, and provide its address to NIC.
Right, but how are they connecting
and
to NIC?
NIC writes, so there you can map the bar 0 register, resource 0. Do you know resource 0?
So they're not going through the kernel at all. They're just mapping the bars from sysfs directly.
Yes. They map a bar 0 and they just write to bar 0 registers.
Right. So I'm assuming that they probably need to disable the IOMMU for that to work.
Yeah, most likely.
I don't.
With IOMMU enabled, I don't think this will work. You will need, with IOMMU, I would say you will need to use any of the available interfaces.
Right.
As Alex said, UIO, IO, and VFIO.
We have tried that in our custom design, and it worked. It's working well.
What version of Linux are you on?
What version of Linux?
CentOS 7.
CentOS 7.
CentOS 7, yes.
Yes, CentOS 7.
Yeah, actually, so the next question is the IOMMU enabled? I guess it's not on by default.
Actually, we didn't enable any IOMMU. Intel helps us using cache to access this memory region. Actually, when we are streaming some data from PCI bus, Intel puts that data to the cache, and when we read it from memory map, we just read from cache, and it is very fast access. So
okay,
we don't
so you guys
need
turned
any
off the
others.
IOMMU to improve the performance. Gotcha.
Yes.
Okay. Well, it also makes it work with the IOMMU off. I think if you turned it on, it wouldn't work at all. Yeah, I'm not sure what the story is with disabling the IOMMU. As far as I'm aware, you might not be able to turn it off on all CPUs. Like Intel seems to be more amenable to turning off the IOMMU on the couple of AMD EPYC-based machines I have here. I think I tried turning off the IOMMU a while ago, and it didn't work like I expected it to. So I might have done something wrong. I'm not sure, but yeah.
Yeah,
Anyway,
I guess it
something to
also
figure out.
depends on how new the processor or how old the processor is.
Right, if it's old enough, it won't have one. Yeah, that's true.
Yeah, the older ones for sure, they have it disabled by default. I think I'm pretty sure, and it really can be disabled.
Right.
But I'm not sure about any new stuff.
Right. Okay.
Maybe 2 cents. I suspect the proxy of FISMAP information you might get tells you what physical address you see from the CPU side, but if the IOMMU is not in pass-through mode, the device may see yet another space of addresses which don't equal the CPU host addresses. So
Yeah,
that
that's
may
a
be
good
yet
point.
another hurdle.
That would definitely complicate things. Yeah.
So for the case where the kernel module cooperates with the user space, then probably an IOTL that gives you a DMA-able memory region would probably be a good way to do it.
Yeah.
Which is the case for Corundum. When you're user space only, then options are more limited. Perhaps VFIO is what they would use there.
Right. Yeah. So I guess there's a couple of different directions that things could be taken in. Obviously, if you want to do something fully from user space without using the standard Corundum device driver at all, then you can use VFIO or UIO or whatever. But I guess the trick is when you do want to use that for just a normal Linux network device, but then poke at your application section and potentially have your application section DMA stuff out of your control application and then send it on the wire or something. Then you want to have the capability to do both. So yeah, my guess is we're going to have to add some ioctls or something else to the device driver and add some some supporting library code to access those. But what those are and what that interface would look like is TBD at this point. I'm not sure what that needs to look like. And I guess there's a couple different directions you could take that in, right? One of them is that you could just request allocation of various regions that are DMA-able from the kernel, and I suppose a different direction you could take it in is to have like a user space buffer, and then you can request that the kernel will pin that and map it for DMA. So I mean, maybe that's just we need to add 2 ioctls for that. Not sure. Might need to take a look at what some of these other interfaces are doing just to see what those APIs look like. Unfortunately, it's not a very high priority for me. So if there's somebody that's interested in poking at this stuff, I'd be happy to work with you. All right. Any other questions? Oh, I see Gray. I'm not sure if you're muted.
Yeah, I've been working on the Linux driver.
Oh, there we go. We can hear you now. Okay.
Okay, and so I got it up to like 10 megapackets per second and 90 gigabits per second.
Okay.
So I'm reasonably happy with that. So I'm seeing if I can squeeze a little more out of it. So I'll probably send in a patch for that as well pretty soon.
Right.
And
so
thanks.
this is for your what have you been modifying here? This is just some optimizations in the driver. This is the memory pools.
Yes, it's the memory pools. I'm modifying the Linux driver, MQNIC
Okay.
driver. So I'll send in a patch for that probably this week sometime.
And I guess you found whatever bug you had the last time around.
Yeah, exactly. I
Complaining
did.
about something
Yeah.
not working right. So
yeah,
okay.
so I figured that out. So hopefully that'll be okay. And thanks a lot for the XUP port, XUPP3R port. That's been very helpful and it's working okay.
Okay, nice.
So far,
I know you
so
asked
good.
something about getting multiple ports working. Is that working for you in the port that I pushed upstream?
Actually, I tried 2 ports at the same time, and that seems to be okay.
Okay.
And so I imagine I'll try the other ports as well. So I'll just connect to the other ports and see if there were all I can get all 4 ports to work at the same time.
Right.
That should be okay.
Okay.
Another thing I've started working on is enabling and disabling RSFEC, right? Forward error correction.
Right. Yeah. Okay.
Right. So I'm hoping that if we like disable this on the Xilinx IP and enable it, that will sort of get it working while it's running. So we just turn on the bit or turn off the bit. I'm hoping that would work. And
as opposed to like disabling it from the TCL file.
No, yeah, I mean, like I want to be able to switch it during runtime, right? So
okay.
I'm not sure if the CMAC has to be reset somehow after the bit is changed, but I'm hoping just changing the bit the CMAX will behave properly when you change the bit on or off.
Yeah, that's a good point. I don't know. We have to take a look at the documentation for that, or we could just try it,
yeah, that's what I was trying to do. And I actually wrote some code in the driver to hook it up to STool. And then I did like a register on the FPGA side to receive the data. So now I can just use STool to actually send the data to the FPGA and get it back. But inside the FPGA, like I had a hard time wiring from the interface to the CMAC. So I'm hoping that, I'll just do like a pull request for you and you can sort of do the wiring inside the FPGA to get the data from one point to another.
Right. I guess we could take a look at that. I think for the CMAC, the way to go ultimately is going to be to have the Softcore handle that in a in a little bit more flexible way, so that the driver can talk to the Softcore and say, hey, turn RSFEC on, turn RSFEC off, or whatever, and then the Softcore would do the right thing. But I think that's going to end up looking pretty similar no matter how you do it, because we'll have some sort of a GPIO register that's implemented kind of at the board level, and then you can poke at that from within the design. So and then it's the question of whether that's connected to the core NIC bar or connected to the Softcore. So it's something I've been putting a little bit of thought into as to what this would look like, because ultimately with the Softcore, I'm not sure it's going to be required for operation. So if you disable the Softcore, then the question is how would the management work? And obviously you wouldn't be able to do everything, but it would be at least useful to do some things.
Right.
The Softcore is mainly to provide abstractions for the device driver. The user space tools, I'm less leery about having them do board specific stuff.
Okay.
If that makes sense.
Yeah, sort of. So, I mean, I don't know Verilog too well, so I just got sort of lost inside all the modules and how they're interconnected to each other.
Right. Yeah, we can certainly discuss that separately or on the Slack channel or whatever.
Okay.
And see if we can get that sorted out. Now that you can actually use the mainline code instead of keeping your own port. Yeah.
Right.
But yeah, I
okay,
think ultimately for all of the 100 gig boards, being able to poke at least the those bits to control RSFEC is useful, because I know that there are some devices that require RSFEC enabled and some that require it disabled. So although usually you don't need to poke at that at runtime, because it's whatever device you're hooked up to, it's going to be one or the other.
Yeah, that's true. Okay, well, thank you. That's all I have.
All right. All right. Any other questions or comments? I don't know if the folks from MLE have anything to say about some of these modifications that I've made for the application support.
To be honest, I didn't have the time to look into it up until now. So
Okay,
the
fine.
modification regarding the app section and destination, yeah, sounds good, and we'll definitely have a look at this. Yeah, we'll have to see how this fits into our current plan of also releasing to the customer soon for the first time.
Right.
Yeah, we'll see. The other thing is regarding the link state.
Right.
If I understood your slides and statements before correctly, then we would kind of yeah, modify the state of our proposal to have a generic vector which goes into such a link state register.
Right. Right. Yeah. I mean, I think what's going to make the most sense for that is just to have like, you know, TX status and RX status. And just that's it, you know, 2 bits for each port.
Yeah.
And then anything more complicated than that, I think it's going to make sense to implement, you know, outside of the core logic, because that could be, you know, much more board or phi dependent or whatever. So that's kind of my thought there. But I can definitely see just, you know, is the receive side working? Do we have a link? We can certainly provide that, I think, centrally.
Yeah, I mean, that's what we kind of need. That's a requirement for us to, yeah, basically differentiate, is something plugged in and is it really working on layer 1, so to say,
right,
or not. That's kind of the requirement. Or to put it from user space perspective, it's basically ETH tool says link up or says link down. That's the point.
Yeah, that's definitely a useful feature. So you know what port you're plugged into and whatnot.
Yeah. Yeah. So I guess we should go ahead and update our proposal then.
Right. Right.
So the structure is okay. Besides this vector topic, the
right.
basic structure is okay.
So the thing is, there's potentially a couple of other port related registers that need to be implemented, and the main thing that I'm thinking we're going to have to put in there somewhere is a few bits related to PFC. Right. So on each port, you might enable, disable PFC, and there may even need to be some sort of a internal TC to PFC traffic class mapping effectively. And that's going to take place. Where is that going to take place exactly? That's going to have to touch the data path closer to the max. So I'm not sure exactly where that's going to. I need to take a look at the top level integration stuff again for that, but that's effectively going to have to sit somewhere in between the, you know, combined TX and RX FIFOs and the ports. So it's not going to go inside of the interface .v module, you know, or somewhere in there, but it's going to go somewhere else. So I have yet to figure out exactly how how I'm going to make that connection. But yeah, so there's definitely a couple things there that need to be sorted out, and potentially there's going to have to be some of those signals that are even translated into the actual, you know, RX and TX clock domains to interface with the max and whatnot. So, and I'm thinking if we have phi status stuff, that would probably make sense to include kind of in that same infrastructure somewhere. So
Mhm,
unfortunately,
mhm,
at this point,
okay.
I don't have a good sense of we're going to implement these registers in this module here, and that makes the most sense. There's some kind of cross module stuff that's got to be figured out. So I'm going to ruminate on that. I don't know about this week because I got like 3 different things going on this week. I'm not going to get anything done this week, but
Okay.
I'll take a look at your pull request as soon as I can and think about where these pieces need to go and how things are going to fit together. And then we can circle back to that.
Okay.
All right.
Yeah, and of course, last statement, Geray, we would be very interested in your improved driver, obviously.
Yeah, I'm hoping to push that as a pull request this week, hopefully.
Yeah, sounds very good.
Okay.
We are very happy about that.
Yeah, it would be good to have somebody else test it as well. So we'll see. And
Yeah,
it's
I
actually
can certainly test it out on my end as well, just to as another sanity check. But yeah.
Okay. Yeah, I'm actually just doing it for the receive side. So I'm not sure if you also need it for the transmit side as well.
Well, I don't know. So the issue is that on the receive side, the driver has to manage allocating all the pages, but on the transmit side, you're getting the pages from the operating system. So I don't really know if you can do an equivalent on the transmit side.
Okay. I haven't even checked the performance on the transmit side. So
right.
I was just my application is just to receive. So I'm just concentrating on the receive side. So
makes sense. Well, I mean, receive has kind of been a problem for Corundum for a while. The performance has not been quite where it needs to be. So it's great you're taking a look at that. Definitely looking forward to seeing what the performance looks like with your modifications. So yeah.
All right. Okay. Hopefully we'll see it.
All right. Does anyone else have any questions or comments? Announcements, anything?
I want to say something. I think the thing in our case was did something called DDIO from Intel. It helps
DDIO,
to
yes,
put,
the data direct IO,
yes,
yeah.
Yes, it helps to put IO packets to cache. I think it was called DDIO something. LLC.
Right. So how do you use that how do you set that up on the hardware side?
On the hardware side, I think we did nothing.
Are you using DDIO with FPGAs now or with like just normal NICs, like an Intel NIC?
FPGA.
Oh, okay, with an FPGA.
The thing I saw on internet was designed for an Intel NIC. It was a NIC, but we customized for our custom design and it worked. So you can, the thing was that we enabled bus mastering from configuration space, and you send, for example, you can map, memory map a buffer memory you can map and send its translated physical address to some location, and FPGA can send data to that location, and it stays on LLC because our device had a DDIO functionality. So I think that's because of that, but I'm not sure. I don't know about other architectures, other CPUs, but
right.
In our
So
case,
the CPU has to support DDIO for that to work. And do you have to jump through a few hoops to enable DDIO on the CPU?
I think we did nothing about that CPU. I don't know.
Interesting.
I'm not sure about that because I'm not a CPU specialist, but what I know is that we just had to enable bus mastering and do start working. You can design anything on user space as you want and just send buffer addresses or descriptors. You can do anything as you know.
Right. Yeah.
Also, you have to remove a driver if it exists, of course.
Right. Right. Yeah. Okay. So you're not even using the UIO or VFIO or whatever. You're just directly mapping the
No.
bars from sysfs.
No,
Okay.
and we don't have a virtual functions also on our PCI design.
Right. Right. I mean, you only need those necessarily if you're, if you need a lot of PCI Express functions and you're going to pass them through the virtual machines and whatnot. So
Yes, you design accordingly as you wish.
yeah, I think we had a discussion about DDIO a while ago. I think there was somebody linked a couple of papers talking about that. I'll have to go dig those up.
And also you have to have a volatile memory, of course.
Volatile
Right?
memory?
But
I mean, as opposed to what?
so you are telling CPU that something else also can change this memory because when you try to
in C. Yeah. That's true. Yeah.
in C, yes.
That's pretty common. You got to tell it to not optimize it.
Yes. If you don't tell it, then it just reads local register. And it says, I did not change this place. So it has to be this and does not becomes too lazy to read the data.
It's like I
Of
read it the
course.
first time. I'm just going to keep using this value I already read because, it's not going to change. Well,
Yes,
that's going to end
yes.
up causing trouble. Yeah.
It thinks that nothing has changed in memory, but actually many things have happened.
Right. Yeah. Yeah, there's definitely, you got to be careful with volatile. You got to put it where you need it, but you definitely don't want to use it too much. All right. Any other questions or comments or anything, or should we close down the meeting for this week? Guess if nobody else has any comments, then thank you everyone for tuning in. It's been a pretty good bit of discussion this week.
Thank you, everyone.
All right.
Thank you.
With that,
Thanks.
I guess I'll see everybody in 2 weeks.
See you in 2 weeks.
See ya.